So you're welcome.
I would like to thank the organizers for very kind invitation. So my work is joined with Vladimir Dragovi, Borislav Gaji, and in some sense is a continuation of previous talk with some differences. We consider nonholonomic problems of the Chaplygin ball type. In the previous lecture, you saw Chaplygin ball with a gyroscope. Now we consider without the gyroscope, and this is the most famous integrable nonholonomic problem in classical mechanics. So just to again recall, Chaplygin ball is a ball that is non-symmetric but balanced. So it has no influence of gravitational force. So it moves like without gravity, but it is not homogeneous. So it's very strange rolling over the plane. And these equations are given for the case of the plane. So gamma is the unit vector normal to the plane. K is angular momentum of the ball with respect to the point of contact. And omega is the angular velocity of the ball. And very well-known system studied by many authors, first, of course, by Chaplygin. And for example, Borisov and Mamayev proved that this system is integrable, but also as a Hamiltonian system because they found some very strange and unexpected change of time and variables such that this system given here becomes Hamiltonian system with respect to this new Poisson bracket. And we can also consider this ball, Chaplygin ball, but now rolling over a sphere. So this we have three scenarios as in previous talk, but now we consider without gyroscopic term. And in all cases, equation for all three models can be written as a single system of equations. So these are almost the same equation as for rolling over the plane. So you see these equations here, first equation for a rolling over the sphere, just to for those who are not expert in nonholonomic mechanics, they are very close to Euler equation of a rigid body around fixed point. In the Euler case, we have the same form of equation, but k d is equal to 0. So you have k is equal to moment of angular momentum act by operator of inertia, but when we put d equal to 0, this term disappear, and these are Euler equations, and they are not that they are Hamiltonian. And here is 1. You see, in second equation we have 1. Here we have epsilon. So very similar equation, but epsilon is ratio depend of the ratio of the ball of the balls. And this is again non-Hamiltonian system in 6-dimensional. In R6 we have non-Hamiltonian system, but it is proved that this system has invariant measure. This is Yaroshchuk. Borisov and Fyodorov find integrable case when epsilon is equal to -1. When epsilon is equal to -1, this corresponds to the case, this case. But we have a spherical shell. This ball is a spherical shell rolling over the fixed sphere S. So this is a little bit strange to imagine. So we have in space some sphere, and somehow that is fixed, and somehow we have spherical shell around this sphere, and it rolls, but with very specific ratio. So the spherical shell have twice the radius of this ball inside. So this is integrable case, and without, if we do not introduce gyroscopic terms and potential terms, these are the two models that are known to be integrable. There are no other models. And our attempts is to produce a nonholonomic system that will, after some reduction, to obtain a similar form of equation, this form of equation, but still additional with some additional modification than in some specific and particular case reduced to these Chaplygin ball problems. So in somehow to generalize all these integrable models within one model, non-holonomic model. And in fact, this is originally we didn't ask for this, of course, problem. We start to consider some non-holonomic system, and as a result, result of our research, we obtained this interesting fact. And this non-holonomic system we studied consists of one fixed sphere S0 surrounded by n balls of fixed radius, homogeneous balls, and over these balls we have another spherical shell. That spherical shell is non-symmetric, so it is like Chaplygin ball. This last part is like a Chaplygin ball. So we have dynamically symmetric, dynamically non-symmetric spherical shell. So we can consider the problem in 4 different configurations. So we have fixed sphere inside, then balls, then a moving sphere, or we can have fixed sphere outside, then balls within, and moving in the last S moving sphere. Also, we can, as in case of a Chaplygin ball, with moving around, like this case, third case, like this third case when we have inside shelling, we also have this. We have S0 inside, then one ball that also spherical shell but homogeneous moving around, and then around S moving sphere. So S0 is fixed sphere, S is moving sphere, but S0 and S have fixed center, and this B homogeneous has not fixed center. The center O1 is moving. So, and another configuration with moving S inside, then homogeneous sphere, and then fixed sphere outside. So it's maybe it is a mathematical model. It is very hard to realize this system in real life, but it looks like in the many machines we have bearing systems. So this looks like usually is given by cylinders, and dynamic over the cylinder is a little bit simpler, but also it's interesting. So we have inside cylinder, then balls, and then around cylinder to load the friction in machines. But this is with spheres, so it is a mathematical model, but similar analysis can be done for these cylinders that have also application. But for us is interesting because of you will see the our conclusions. So just to fix the notation, E is moment of inertia of the moving sphere, so dynamically non-symmetric. Omega is the angular velocity of moving sphere in the moving frame attached to the sphere. We have n homogeneous balls with so this is moment of inertia is simply multiplying by scalar I. I is in mass of the heat ball, and the angular velocity for this ball, we take angular velocity in the fixed frame. So in the frame S0, so with the with respect to the ball S0, and we have unit vectors determine the position of the center of the balls in the fixed frame. So gamma is directed for gamma 1 is directed in this direction, gamma 2 in this direction, gamma 3 in this direction. So to the sphere. The configuration space of the problem is so Lie group SO3 over 1 plus 1. So these are position rotation of these n balls. G1 to Gn, these are n balls. Position, these are matrix, SO3 matrices. And G is a position of moving sphere. Gamma 1 to gamma n are a direction of the centers. So this is very huge manifold. And kinetic energy of the problem, so we consider without potential terms. Kinetic energy of the problem is given by kinetic energy of the moving ball, kinetic energy of the homogeneous moving non-symmetric ball, homogeneous spheres, and moving. So this is according to translation, kinetic energy of the translation of the balls. Velocity are given by gamma by this formula. So we have some notation with plus and minus to consider all cases together. So here just is important to mention that how obtain. So this is until now we didn't impose nonholonomic constraints. But our constraints that the velocity of the point of contact are 0. So we have this A point of contact with of the balls with S0, and B's are the point of contact with S. And S0 is fixed sphere, so velocity of this point of contact should be 0. But sphere S, this surround sphere is moving, so velocity are not 0, but we have condition that velocity of the sphere S and this homogeneous ball at the point of contact B1, B2, and so are equal. So these are equality of the velocity. Here we have zeros, and here we have equal. So we have non-holonomic system without sliding. So balls do not slide over the sphere. And this is a condition for this non-holonomic condition. And just to mention that configuration space of dimension phi n plus 3, we have 4n independent constraints in velocities. So our distribution is of rank n plus 3. So in every point of the manifold, we have n plus 3 direction where we can move. And the system is have a very big group of symmetry. This is SO3n plus 1 action defined by this formula. So we have combined action from the left and from the right. Left action, A, so is an element of SO3, corresponds to choosing, we have a freedom of choose moving reference frame attached to the ball, moving ball. And A1 to AN matrices are going to say that we have freedom in choosing reference frames, not of the moving ball, of the fixed S0, because S0 is fixed. So we original reference frame is we can take arbitrary. And A1 to AN we have a freedom in choosing reference frames attached to the balls because they are homogeneous. So we have combination of left and right action. It is interesting. In the rigid body dynamics, usually we have one action, but now we have a combination of two actions. And this is the reduced space. After this reduction, it can be proved that this space is of this. So we obtain all object considering a moving reference frame. Omega is angular velocity of the sphere, so dynamically non-symmetric, and omega 1 to omega n angular velocity of the homogeneous balls, also in this reference frame of sphere, and gamma 1 to gamma n direction of the center of the spheres, but considering in the reference frame attached to the moving sphere. And in these coordinates, we can write constraints in this form. It's very nice form. And as a result, we obtain so on this is quotient space, and these constraints are also invariant with respect to the group SO3 over m plus 1. And this is our system is reduced to this M. So this is reduced space of our system because both Lagrangian is invariant, or kinetic energy, and distribution. And we can consider this motion on this reduced manifold dimension 3m plus 3. So this is first observation. And then when we write equation of centers of the balls, we obtain this form of equation with epsilon. These are epsilon is defined here. So like a Poisson with epsilon equal to 1, this is standard Poisson equation in rigid body dynamics, but we have here epsilon, different from 1. And equation of the sphere, moving sphere, can be obtained by using standard equation of the moment. So by FB and FA, we denote reaction forces, as these are the standard Newton equation in a vector form. So we use, instead of Lagrangian, we derive the system by using standard Newton equation in a vector form. From these equations of motion, we obtain the first integrals. So projection of gamma to omega to gamma e. So projection of angular velocity of the heat ball to the direction of the heat ball is constant. It's very nice integral. And the second integral means that the rolling balls, these small balls, do not change position between themselves. So if they form, for example, some tetrahedra, if we have 4 balls forming tetrahedra, they will always form this tetrahedra congruent to the original configuration. So like tetrahedra of the balls moving around the fixed sphere. And the first condition constraints are very interesting, because if we put the first condition equal to 0, these are very well known non-holonomic constraints called rubber constraints. So sometimes in some non-holonomic models, we put these constraints to forbid rotation around the point of contact. If we put S equal to 0, the small balls the small balls, homogeneous balls, cannot rotate around the point of contact. So like they are rubber. So these and now so C is we can fix. So C, when put C to be constrained, we obtain the motion on MC, and on MC we can solve omega angular velocity of moving balls in terms of omega angular velocity of non-homogeneous sphere and point of and direction of the centers. So as a result, the problem additionally reduced to this space n. So we have as independent variables only omega, gamma 1 to gamma n. So now we drastically reduce the configuration space we studied. So this is a very interesting geometrical situation in previous considerations. So this commutative diagram describes what we do. We have configuration space, this big one. Then we have constrained submanifold, and we have constrained submanifold with integrals. This is reduction by SO3 m+1 action. In these three directions, we have this reduction. This is without constraints manifold, M is with constraints, and this is with additional integrals. And then we have additional we explained in the previous slide that this MC is in fact diffeomorphic to just this product, and we consider the problem on this space R3 times S2. It is when n is equals to 1, it is 5-dimensional space. And if we set M to be I omega, where we have I omega plus this very huge term, and vector n by this term depending of constant and direction of the balls and moments of the balls. So this just to, in the case of Chaplygin ball, just to recall, we have angular momentum of the ball with respect to the point of contact is angular momentum of the ball plus some term. And here we have a similar situation, but with more terms. I'm sorry. With more terms. And we proved that our system is reduced to this set of equations. Very nice set of equations. When epsilon is equal to 1, this term disappear, and it looks almost like Euler equations. And we can write the equation also in this form, where if we put m here on the sum of m and n. And we proved that our system has invariant measure. So this is the invariant measure of the problem. And always has the following integrals. So we have invariant measure and a set of integrals. And in special case, when n is equal to 1, we have 5-dimensional space, invariant measure, and these two integral. So this is the sphere, just one sphere. This we do not count this third integral, but we have the first two integrals. And for integrability, we need additional one integral. And we write in more detail this situation with one ball. So equations of the form given here. And with m is equal to m plus n, so this is m. I'm sorry for this notation, but I hope that this is clear. And we prove the following theorem. When epsilon is equal to -1, this is the configuration 3 for 2r equal to 3r. We get the following statement. The spherical ball bearing problem in the configuration 3, the radius of the moving sphere is twice the radius of the fixed sphere, is integrable. The third integral is, so we have complete integrability by means of Euler-Jacobi theorem. We have 5-dimensional configuration space with 3 integral and invariant measure, it is integrable. And when d equals, so we have some parameters. Here we have some parameters, d and d. These, when this parameter is equal to 0, our system exactly reduced to the system found by Borisov and Fyodorov of the Chaplygin ball over a sphere. So this is direct generalization of this system. And we have a second integrable case when b equal to c and generic epsilon. So when we have symmetric case, we expect something like netted theorem, but it is not. This integral is not from netted theorem because it is not algebraic. We see we have exponential term, and we have in fact 2 integrals, but they are dependent of others integrals. So actually we have just one new independent integral, and complete integrability also in this case. And I would like to thank you for attention. I'm sorry, maybe 2 minutes. Oh, 27 minutes. Okay, I have 3 minutes more. I'm sorry.
You have got 10 minutes more.
Okay, I passed. So I pass another system. So we have this is another problem. We have another problem we solved also. So the planar ball bearing. So imagine that sphere, inside sphere and outside sphere radius are going to infinity. And as a result, we obtain one fixed plane, sigma 0, and then moving balls over and moving plane above. So this is planar ball bearing problem. And it shared many common features of spherical ball bearing problem, but it's different, of course, system because it is a very singular limit. We cannot directly apply all the results in this case, and we need to analyze as a separate system. And just to mention that this system also have invariant measure, and we prove integrability for arbitrary configuration. So just to mention, we introduce vector n and m in this way. So O is fixed in the moving. We fix the point in a moving frame. B a point of contacts, A a point of contacts with same definition of nonholonomic constraints. And for a configuration, for a coordinates, we can take so this vector in the moving frame, the vectors obey are coordinates of the balls, and we define this vector n to be this sum. This is some kind of looks like delta E are some parameter like center of mass of the balls of this point with weights delta E, and m is this sum, and also here x and y are coordinates of the point O in a fixed frame. And when we put all this together, it can be proved that our system can be reduced to system with coordinates, phase space of the problem is when this Vx, Vy, V theta, this is velocity of theta is rolling of outer sphere, n1, n2, and m. And we have this algebraic condition, and we prove that this system is integrable and solve in quadratures and final invariant measure. Just for us here, what is interesting that the system reduced to some algebraic subset of R6. So it is given by this equation of paraboloid, upper half of. So this is I would like to thank for your attention.
Thank you very much. Very interesting talk. Perhaps any questions, comments, colleagues? Well, I have got a little question. Is there any connections with Celtic stones, or they're also known as wobble stone?
Yeah, of course, there is a connection. So they are all nonholonomic problems. Celtic stone is a very interesting nonholonomic system. This is the rolling of ellipsoid with very strange mass configuration over the plane. And when you can see that in one, so the future of nonholonomic mechanics and nonholonomic these constraints is when you rotate in one direction, it is stable rotation. But if you rotate in another direction, this ellipsoid, it will be unstable. And it after some times, the stone will start to turn direction of rotation and go to the direction of stable rotation. So it's this problem is non-integrable. Celtic stone is non-integrable. Here we studied, but of course, it's from a point of view of mechanics, one can study stability of, and it can be, this property of Celtic stone can be proved analytically by using Lyapunov theorem.
Okay, thank you. Any other questions? No, then thank you again. The next speak